Good morning or good afternoon, as the case may be. Thanks for joining us today. This is a review of topic modeling techniques using Python and a couple of sklearn and gensim libraries primarily. And we're looking at different clustering techniques that allow for the extraction of latent topics within textual corpus, right? Within a document, really a set of documents. So a little context is necessary. I'm going to try and fit this into 15 minutes, but it's probably going to go a little bit longer. I have a couple of artifacts that I do want to go through. And I've also got some GitHub and a Jupyter Notebook file that I'm going to sort of walk through, which is the extent of the presentation, more or less. But so a little bit of context, because this isn't necessarily topic modeling as it's looked at in current research. So my interest primarily is in metaphysics, and it's metaphysics primarily, but I have a background in computer science and systems engineering. I'm a second-year PhD candidate and in computer science. And my original foray in this topic was going to be on ontology learning, which is the ability to extract hierarchical concepts from a given text using unsupervised and supervised learning techniques. That exercise proved to be extremely challenging, and I do have some work that's going on with someone that I'm working on overseas to try and prototype some of those models. But that usually involves, as it turns out, studying literature involves putting together and layering several different NLP modeling techniques together, whether it's relation extraction, topic modeling, and ultimately ending up with concept hierarchies. But so as a stepwise approach to that, what I looked at is to say, okay, let's look at the topic modeling techniques themselves and see what kind of algorithms are available and what kind of output we get when we try and extract a set of topics from a corpus of documents, right? With NLP, it's usually looking at not just a single document, but a corpus of documents. Most of the algorithms have been designed to be able to extract and parse thousands, if not tens and hundreds of thousands of documents, normalize all that text, feed it into a model, and then come up with a set of topics that could be used for document search primarily, and information retrieval, which is primarily what that particular research domain is not only called, but what is focused on. It's information retrieval. Okay, we're looking at something slightly different here in this study, what I call a clustering and topic modeling study. What we're looking at is for a given text, a large sort of philosophical and or theological text itself. If we apply some of these machine learning models to that text, what kind of topics come out? And it's a somewhat different problem. And we found, certainly when we looked at some of the underlying models that apply to this field of research within natural language processing, not all of them were applicable. For example, BERT topic only would give me 2 topics for all of the text that I was using as an example, because my corpus only included 57 chapters. And it's primarily looking for thousands and thousands of documents. We only had 57. So the text that I use, and I'll pull it out here so you see it, which I have. The text that we use for this study, okay, is a book actually that I wrote, which may be backwards for you. Eurasian Philosophy and Quantum Metaphysics. It's a very long text, actually, which is a sort of a philosophical and or a theological work, which looks at the development of theology and ultimately metaphysics throughout history. And there are a couple of advantages with working with this. First of all, I own the text, so I own the IP. I have a text file that I can then extract into chapters. But I wrote it, which means I know what the topics are. And I'm also, because of the way it was written, the chapters themselves are actually very demonstrative of the underlying topic in the chapters. So it's actually quite a good test text to determine what these models are outputting, whether or not they're good or bad. This sort of eyeballing technique, and we'll look at some of the clustering techniques further on. So without further ado, I'm going to walk through. I have 3 artifacts here. I have a presentation which I'll walk through briefly. Let me share my screen now so you guys can see what I'm looking at. So I have a presentation here, the notebook file, which is primarily where we'll be spending most of our time. I have some outputs, and then I also have a GitHub repository, which is also included here, which includes this code, and all 3 of those will be uploaded along with this presentation. Okay, so without further ado, let's look a little bit at just sort of the scope of the work, right? So, when we look at, machine learning and artificial intelligence and NLP, it's important that we have somewhat of a context, right? As you can see here, that machine learning and deep learning are all leveraged as part of the NLP domain from a research perspective. Topic modeling sits inside of the NLP and has is very, very deep topic. In fact, no pun intended, but certainly much deeper than I expected. There's a lot of sophistication in some of these models and a lot of underlying mathematics, and much of that you need to really understand to really optimize and build these models. And we'll go through certainly some of that. A couple of slides here with respect to the history and the development of NLP. With respect to deep, some of the deep learning models, and then of course GPT-3 and 4, which just came out, which are based on some of those models. BERT, which I already mentioned, and this idea of pre-trained language models. Some of that is sort of tangentially related to the topic at hand, but not primarily. We're using more sort of core clustering techniques, which we'll get to. So when we look at topic modeling, text corpora modeling, right? So we're looking to summarize the text, right? And we're also looking to identify a geometric space through which we can determine similarity, right? And that's the way primarily that this information retrieval is able to work and to function, right? And this is a massive area, right? Google PageRank is one of the things that are in this area, and a lot of the search capabilities that are sort of ubiquitous in tech right now are based on this sort of information retrieval NLP research area, of which this is a sort of a sub area, you could say. Some of the approaches that we're going to look at are latent semantic analysis, probabilistic latent semantic analysis, latent Dirichlet allocation, and then k-means, NMF, and hierarchical clustering techniques. Okay, those are some of the things that we're going to be looking at. So, I mean, ultimately, you have to, the first task at hand is you have to vectorize this particular text. Machine learning models really only understand numbers, ultimately. So you have this sort of massive area in NLP of extracting information, text from text files, into basically vectors of numbers that represent the text, that which in turn get fed into the models. The two that we're going to be looking at here in detail, the bag of words, which is just basically for each document, which words show up in a count. And then this notion of TF-IDF counts, which includes a factor which allows for a uniqueness property of the words in a given document to come out. So it sort of normalizes all of the words themselves. And if the word shows up in all of the documents, it's not very unique to that given document. It's sort of normalized out using a mathematical equation, which we can take a look at. Text classification and versus topic modeling, they're related. but they are definitely not the same thing. All right, so we get into clustering techniques here. The first one that we look at in depth is k-means clustering, which is actually quite effective. And what this does ultimately is it starts out with a random set of clusters, and then in the space that's been defined for these given documents, it starts gathering basically all of the nodes in these things called centroids, and then it basically comes up with a set of clusters of data and information that in turn can be related to topics, because you get a bunch of words that are related to a given topic, and you'll see some of the output. This will make more sense. And this again is another example of how this sort of works through iterations of the algorithm. And this is sort of surprisingly effective, even though it's, I don't want to call it a simple technique, but it's fairly straightforward. Hierarchical clustering is slightly different. The output there is basically it builds hierarchies of topics in the text as it go. There's two different ways that it's doing it. It can start with basically top down or bottom up, more or less, and there's agglomerative and divisive. And we look at some hierarchical outputs there. Also effective, but the output is different, and certainly the approach is somewhat different. And then the other clustering technique we look at is non-negative matrix factorization, which looks somewhat like the latent semantic analysis, which is based on singular value decomposition. Both of them are mathematical techniques that deal with linear algebra and matrices, and basically take a given matrix, which ultimately, right, is what we're representing the text with, and then breaks it up into components. And those components, right, those factors, quote unquote, end up yielding significant information with respect to topics or areas that are representative of the text itself. And I won't get too much into the math, but some of that is actually in the Jupyter Notebook, which we're going to look at. The two most common techniques probably that are used, at least certainly in the literature, latent semantic analysis and latent Dirichlet, I'm probably crucifying that poor man's name, Latent Dirichlet Allocation. Those are probably the two most common. Latent semantic analysis is based on singular value decomposition, which is another sort of a matrix factorization technique, which allows for the elicit of topics in, again, a matrix of data. And we'll see how capable that is when we go through some of our examples. There's a sort of a dovetail, a related way of approaching SVD, which is also truncated SVD in some of the libraries that we look at. And the probabilistic latent semantic analysis was generalized, okay, to latent Dirichlet allocation. And this in turn looks at probability distributions of a given document with a given set of words, and then sort of splits that out, and then basically optimize it with a certain set of calculations. And that in turn yields, again, a set of topics. And the mathematics is also spoken to a little bit here and in the notebook. So with that, with the presentation, those are the presentation materials which will be released as well. Then we'll walk into the Jupyter Notebook file. So this follows pretty much the same model. It just has we look at a specific text file, which again is that text in digital form, and then we basically split it into chapters, okay? And we can see from, if you sort of look at, let me just pull up the chapters here so you can see what we're looking at. So here's the chapter files, right? So we took the text file, and then there's actually a split function here. Yeah, here it is, which just basically looks for each one of the files on record. There's also there's code in here which actually takes the initial text file, which is also on the GitHub, and then splits it up into these chapters based on looking basically for empty spaces between the chapters. And you can see here, it's fairly straightforward text. The notes aren't there. Most of the text is in English. There are some keywords from different languages when we look at some of the Sanskrit and the Chinese terms and how they're transliterated into English, like these, for example. So there is some level of awareness and code that needs to be done to extract those terms effectively, and you'll see that. So the first thing that we do here, by the way, is we load all the data, and then just as sort of a smell test, we actually do a word cloud, which says, okay, for each one of the chapters, right, what are the top 20 words? And then for each one, we actually do a word cloud of that. So you can start to see, just even from a basic, word cloud representation, you can start to get a sense as to what each one of the chapters is about. It's also worth noting here that when you look at this output, where did my, let me go back here. Topic modeling, output, no, topic modeling, data, chapter docs. And this is part of what is relevant here, because when we get the output, you can actually see, these chapters are pretty descriptive. And that's done really by design. And that's one of the things that allows us to look at some of this output and just really through through eyeballing determine how effective some of these algorithms are. But again, and it's worth repeating, the approach that we're looking at in a large text itself that's divided into chapters is somewhat different. It's significantly different from the information extraction or information retrieval problem in Toto, right? So because of that, some of the models work differently, and you'll see some of the output as well. Some of the models really aren't effective at all because they're designed to work on, tens or hundreds of thousands of documents and model them in a way where you don't really know what the topics are supposed to be beforehand. So this particular study is slightly different there, and you'll see how that dovetails into the approach. So we do a little bit of preliminaries here from a mathematics perspective. I won't go through that, but that is here. The term frequency, inverse document frequency algorithm is here, and a description, as well as singular value decomposition, which underpins latent semantic analysis. You can see how that's done. There's also an example here using NumPy libraries that shows exactly what that matrix yields. Now, this becomes important because you really need to understand how these matrix factorizations work, because we're looking at output numbers and we want to be able to interpret them. And you'll see that in a little bit when we look at the LSA numbers and the LDA numbers. Dirichlet distribution, LDA, has its own algorithm overview as well as mathematical underpinnings as well, which is based on probability distributions. And I won't get into that, but it's really fair to say, and then again here for non-negative matrix factorization, same underlying mathematics, some linear algebra and matrix mathematics, and as well as the clustering and the hierarchical clustering, k-means and hierarchical. All of them are sophisticated models in and of themselves. If you're a mathematician, you're going to be comfortable sort of moving, or a statistician, you'll be comfortable moving around in these models. But if you're really trying to understand the output and be able to interpret some of these things, you really have to have at least a basic understanding of the math. Which I ultimately do, but still it's a very deep area in and of itself, particularly when you're dealing with many of these models. So, some of these models, k-means, for example, has, half a dozen different approaches. Hierarchical clustering, for example, has a half a dozen different ways of measuring distance between points, right? So each one of these models in and of themselves, you can sort of explore and do independent research in. So that's here in the notebook file. I would also, it's also worth pointing out that you can run this. We've just set this up to run either locally on a VS Code or on a Jupyter notebook file, whichever is more convenient for you. The only change here, if you go up to the utility functions and components, is the collab equals true or false. You set that into false, the variables play out, and it's been tested on both platforms. So from a GitHub perspective, there's value there. If you're interested in topic modeling, and you're interested in looking and extracting and analyzing texts themselves, dividing them into chapters, and that becoming your corpus, this is certainly a good place to start. I should mention here, there's like probably 40 or 50 sources that I've used. When I look at the code in particular, I've tried to specify, and certainly some of the images, what the sources are, but it's embedded in the text, and hopefully will be of value here if you have a different, if you're looking to work with the code itself and look at where it came from and what principles it's based on. So now we get into the specific examples. So let's walk through the code. So the first thing we look at is we look at k-means clustering, and we have a bag of words model initially, and then we use a TF-IDF vectorizer, and then we kind of compare and contrast. Okay, so we'll look at, this is the bag of words model that we use. This is the call here to build the k-means clusters, and I'll increase the text here a little bit so you can see it. You can see here it's pretty straightforward, but there is a model. There's a random state here. Not every run is the same. And then we have a consistent format, output format. You can see here that the number of clusters that we're working with is 5, from 0 to 4. And that number is primarily because, again, I understand the text. 5 is probably a good number to work with. And you can see with the bag of words model, a lot of this is bunched into cluster 0 and cluster 2. You could see that there are key features here that are identified for each cluster. This is consistent throughout. And we're looking at the top 10 terms. And then you can see the list of chapters. So generally, again, you could see based upon these chapters, you could see that there is sort of a decent mapping that occurs, but it's fairly generic here with the bag of words model. Now, if we go to the vectorizer approach, we're creating a TF-IDF vector structure. We're defining a distance measure based on cosine similarity, which we'll use below. And again, we're setting up the k-means cluster. And then you could see with the TF-IDF, there's a sort of a much more natural split between the two chapters. And if we compare them side by side, because we write all these outputs to a file, okay, this isn't from the, I think it's from actually the same run, but I did save these beforehand, just so you know. You can see the terms themselves, right, are certainly different for each cluster. But you can also see that some of the more generic terms, which makes sense given the distinction between TF-IDF vectorization and bag of words vectorization, some of those generic terms are removed, and therefore it sort of allows for a more a clean split between the different clusters. So now how this is output, and this is worth and important to really understand, is you effectively, what all of these models do, we normalize the corpus, okay, which I guess it's important to at least look at that, okay. We have stop words here, and then we lower, we strip, and then we normalize the TR corpus. This is what it looks like actually in the vector before it's set to numbers. this is kind of what it looks like. It's divided into 57 chapters. Each chapter is a doc in the corpus, and that in turn is what's fed into the model. The first, again, the bag of words uses a count vectorizer and then extracts an NP array, which is then fed into the k-means cluster, from which the topics are extracted. Same model here, except we're using a TF-IDF vectorizer fed into the k-means cluster, and then we're writing the output. For the hierarchical clustering is interesting, and I do have the output here, which is of relevance. And you can see it takes a very different approach here. And primarily when I'm ballparking these models to see which ones work, the ones that I look at are the ones from China. There's about 5 or 6 different chapters here that are based on ancient Chinese philosophy and theology, and those need to be and should be grouped together, right? And you can see here how even in the hierarchical format, these chapters are in fact grouped together, which is what we would expect. Now, this one it got wrong. Chinese philosophy, right, is sort of outside of, I shouldn't say wrong, but it looked at that and it grouped it within a sort of a larger sort of philosophical lens, whereas the Chinese philosophy themselves were grouped together as we would expect, right? And you can see that not with the bag of words model, but you can see that come up a little bit more with the TF-IDF. You could see again here you've got these 6 chapters which are basically mapped to ancient Chinese philosophy, which is again what we would expect, and that's a sort of a hallmark benchmark of how I'm able to determine whether or not these things are doing what I would expect them to do, let's say. Let's see, chapter models, but relatively straightforward once you get the normalization done and you're able to get the underlying data structures together. There's not a lot of code that you necessarily need to write, but to get to this place of this simple code, no doubt took quite a bit of time. The next model that we use is an NMF model. You could see here that in the NMF model, it has a clear probability distribution for each chapter, which is convenient. And also LDA actually has a similar output that tells us basically the strength, the probabilistic strength, more or less, for that particular topic, for that chapter in that particular topic. So, and all of these outputs, by the way, once the model is created, what it does is it walks through each of the 57 chapters and feeds it into the created model. Okay, so even though it's seen the chapters themselves before, because all of the corpus of documents, all 57 chapters are fed into the model, what you then do is sort of a benchmark, and you would expect it to do well, is we feed it data that it's already seen before. We feed it each one of the chapters and say, hey, what's the topic that is most likely for that particular, given that model for that particular chapter. And non-matrix factorization here, we have some output here as well. It does a pretty good job, surprisingly. Probably slightly better than I would say of TF-IDF and k-means. You can see here, this is another area which is also easy to tell whether or not the model is doing what it said. We do, from a metaphysics standpoint, we look at a lot of quantum mechanics and relativity, and there's a bunch of topics here, chapters that relate to that. You can see that it flagged those and did a nice job there. Same thing for, there should be, yep, there's a Chinese cluster here as well. We get the same, let's see, 6. We pick up, this actually picked up the ancient Chinese philosophy one. So this actually, I think, did a slightly better job there. And then you can see what the other chapters look like. So NMF actually did quite a nice job here, what I would expect. which is, a relatively straightforward clustering technique, but nonetheless, it did a nice job. So now we get into what are more sort of the industry standards, latent semantic analysis, and LDA. Everything that we did prior to that is really prep for these. In the literature, this is what's really looked at as this sort of benchmark study. So you can see, again, we're dealing with 5 topics. You can see what it came up with. The topic list is a little bit different. And then again, it has a set of what you might want to call probabilities, but they're not necessarily the same thing. For each chapter, you can identify for each topic what the likelihood is, and the maximum value there ends up being the topic that it's quote unquote assigned. But the probabilities are important because in information retrieval, primarily you're looking not necessarily at the best, but if you have a query, you want to find all of the documents and rank them. So the fact that you're mapping each one of the docs, quote unquote, which is a chapter here, into the model for each one of the topics becomes important and relevant as you're doing information retrieval. It's not necessarily what we're designed for, but that's why some of this data exists. And again, we have a similar output here, and we go through a similar algorithm to get the output. We have a model that we're using, LSI model. This is the bag of words. And then we have, so we looked at k-means bag of words. Yeah, we looked at k-means bag of words. We looked at k-means TF-DIDF. And then we looked at TM and MF. Okay, so now we're looking at the LSA bag of words, which is the code we just looked at. And then we're looking at LSA TF-IDF. And you could see here from the output, despite the fact that it maybe pulls out topics that we think are relatively reasonable, when I feed the chapters back into the LSA model with bag of words, it just throws everything against the first topic. So not very useful for what we're trying to do, actually. And I don't know whether or not that's because there's a problem with my code or not. I looked at this and ran it several times, but that model just doesn't seem to work. Now, when we use a TF-IDF vectorizer, okay, again, we're using the gensim models here, but when we use a TF-IDF model, we get a little bit better map. And so here you could see the output for the TF-IDF model for, again, latent semantic analysis, which is predicated on singular value decomposition. You can see for each topic, again, for each chapter, it lays out for each topic. Now, one of the things about latent semantic analysis is you could see the relative strength, right? So, for example, this introduction topic, right? That chapter maps to ultimately the first topic, right? Which is this one, okay? Okay, but there's, these are relative values, but they're not really very meaningful in terms of percentage or anything like that, all right? But the values have the relative strength, and that's one of the characteristics of latent semantic analysis. But you can see with the TF-IDF, it doesn't do a terrible job. Here's again the sort of scientific metaphysics sort of view, and you can see that a lot of the right chapters are plugged in here. You can see there's an Indian philosophical section. It picks up on that pretty well. You can see some of these terms that it's used. Interestingly, this particular run didn't classify the Chinese philosophy into a separate. Yes, it did, actually. Here we go. But you can see from the terms here, not very descriptive. So there's some optimization challenges here, let's call them that. Some of that may be the function of the code, but I'm pretty sure this is mostly right. So it groups them properly, but the key features terms, once you extract all the ones that are found in all the documents, right, which is what TF-IDF does, you end up with a little bit less description here. For example, So certainly as it relates to like NMF, it's not really doing nearly what we would expect it to do. Now, it may be very good at information retrieval necessarily, but in terms of representing meaningful topics, I think this LSA model, I think, is probably one of the weakest. So now we get into LDA, and let's look at the LDA output here. Let's sort of jump to LDA uses bag of words. It doesn't use a TF-IDF vectorizer, and it does that by design because it does a lot of some of that same work in its underlying mathematics. You can see most of the stuff is grouped here in the first tier, this first section, which is fairly generic. Let's see if it here we have some Chinese distinction topic, but it doesn't do such a great job in terms of categorizing that. We do a couple of different examples of LDA here, but you can see again with LDA you do get more probabilistic representations of each given chapter and each given topic. Not all the topics are represented, but you can see here that these add up to 100%. So it tells you, which is quite convenient, what the percentage representation probability is that given chapter yields that given topic, which can be very useful and is just coherent, so to speak, which is a word I use a little bit further on, but it makes sense, which is good. And then here's our output, which again is somewhat lopsided. But with LDA in particular, we get these nice sort of visualizations, which is this L Davis, pi L Davis representation. And you can see here for each topic, you could see the words that are relevant for that particular topic versus the overall term frequency. And you can see here that, this one is the biggest, 2 is the second biggest, and this is representative when we look at how the topics were distributed. Let's see, this is 5. So you could see here that the terms that it picks up are quite good, but somehow it's miscategorized, I think, a bunch of those chapters once we feed it back into the model. It's possible that my code has a bug, but certainly it's a little bit odd that it's not doing categorization that I would expect it to do. The model does not seem to be very effective. There's a couple of different features here in terms of breaking out different sentences and keywords. I won't get into those. There's a fairly long representation here that we use to try and optimize the model. I do want to cover this briefly, although it's not terribly relevant. But if you don't have a good understanding of your underlying data and your corpus, and you're trying to figure out which model parameters, quote unquote, are the best, for example, how many topics you want to use, there are various methods to do that. We go through that here. There's some coherence measures that are looked at. And based upon that, what we do here is, this is LDA 2. No, this is, let's see, this is LDA 2. Let's see where you are here. Which is ultimately, it should look pretty similar to this, but it's still slightly different. Every time you build an LDI model, depending upon your parameters, it would be slightly different. And you can see here the way the chapters are breakdown out. It's the same sort of problem. There's some miscategorization that's involved. There's one more LDA example that we do here. You can see how now we want to turn it. We want to tune it using the hyperparameters. There's an alpha, there's a beta parameter, and there's certainly the number of topics. And we want to try and find the optimal set of parameters. And we do that by effectively iterating through. This is a technique in machine learning that's pretty common, using k-fold analysis, for example, just walking through all the different parameters using a particular score. We use a coherence score here, and we could see from the output what the max coherence score is. We print out the top 10 here, and you could see what the values for alpha and beta and the number of topics. So this particular study ends up with 4 or 5, which is interesting because some of the values I got were up in the 8 to 10 range. And then with 5, we build the model, we'll build another model, and then we use the specific parameters for alpha and beta. And then we go through the same exercise, and we end up with output that looks something like this, which again is fairly lopsided. And again, we have that lopsided value is reflected in the charts here as well. I think that's ultimately the extent and scope of certainly the artifacts that we built. What I will say is, as we look at topic extraction, topic modeling within the context of analyzing a given corpus, like the Bible or the Quran or some of the other corpuses that I'm interested in extracting meaning from them, quote unquote, using unsupervised learning techniques, such as all of these are unsupervised. It takes the data itself and it extracts basically a meaningful grouping as a function of the distribution of words in a given document. That's basically what all of these techniques are doing. There are certainly some of the methods which are more, let's say, more intelligent than others, right? And some of the basic clustering techniques seem to have outperformed LSA and LDA within the context of at least this study. And so with that, hopefully this is of value. I will also have the artifacts themselves, and the links will be underneath the video, so that it'll all kind of be grouped together. And hopefully this was instructive, and hopefully you have a very nice rest of the day or evening, as the case may be. Thanks very much for staying with us, and we'll talk soon. Thank you. Bye.